Hello everyone, welcome. I'm the student of Sri Venkateswara College of Engineering, Bangalore, from the Department of Computer Science and Engineering. The subject is Theory of Computation, and the topic is Fast Practical Comparison of Deterministic Finite Automata. DFS are the fundamental computational models with a wide range of applications from the text processing and the pattern matching to the network traffic analysis and the malware detection. However, as DFS grow in a complexity, their memory footprint can become a significant bottleneck that limiting their practical use. This paper represents a fast and efficient algorithm for the compressing DFAs and enabling the deployment in the resources constrained environments without compressing the performances. The basic idea is to maintain the collection of regular expressions called signatures that corresponds to the malicious content, violations of the security policies, and etc. And then the match of collection of the signature against the input. In the typical scenario of the throughput network traffic, the matching must be fast enough to process the input at a network's speed. A natural approach to solve this is to construct a deterministic finite automation of a collection of signatures and then the stimulate it on the input. The DFA matches each character of our input, which is single constant time state transition and requires only single memory access. Comparison of the deterministic finite automata is an important optimization task, especially when working with the large scale states machines in the field like text processing, network security, and the artificial intelligence. The goal is to reduce the memory footprint and sometimes the processing time of a DFS without losing its ability to accept the same language. Introduction to deterministic finite automata. What is DFA? DFA is a deterministic finite automation is a mathematical model of computation that can be used to recognize and process the patterns in a given input string. It consists of a set of states and the set of input symbols and the transition functions or a start state and in a set of accept state. DFA works starts in the initial state and reads the input string one symbol at a time. At each step, the DFA transitions to a new state based on the current state and the input symbols following the transition function. If the DFA reaches an accept state after processing the entire input string, it accepts the input, otherwise, it rejects it. The applications of DFAs. DFAs have a wide range of applications, including text processing, pattern matching, network traffic analysis, and malware detection. They are often used as a underlying model for regular expressions, which are essential tools for the tasks like string manipulation and the data validations. State minimizations. This is a classic approach to DFA comparison and involves merging equivalent states. And this exists in a unique minimal DFAs that is up to isomerisms that recognizes the same languages and the techniques like Morse algorithm and the Hopcroft's algorithm that were used to find the minimal DFA efficiently. Table comparison. The table comparison of a DFA that can be very sparse if the DFA has many states but only have few transitions between them. Sparse representation like the row displacement method or a delta encoding that can reduce the memory usage, compressed storage, and the bit packing are also practical for the reducing of table sizes. Run length encoding and the finite state and entropy coding. If there are long sequences of states with the same transitions or patterns, run length encoding can compress these sequences. More advanced entropy coding techniques like Uffman's or arithmetic coding that can be applied to the transition table to exploit the statistical redundancies in a state transitions. Motivation of a DFA, the memory footprint and the performances impact and the storage transmissions. The memory footprint. As a DFA grow in a complexity, their memory footprint can become a significant bottleneck, limiting their practical use in a resources constrained environments like a embedded system or a mobile devices. Performances impact uncompressed DFEs that can be lead to the slower processing times that can be increased power consumption, which is especially problematic for the applications that require a real-time or a low latency processing. Storage and the transmission, storing and transmitting large uncompressed DFEs that can be a challenge, particularly for the applications that require distributing the DFA models across the multiple devices or servers. Challenges in a DFA's comparison. Preserving functionality. It balances the comparison between the ratio and the speed, and it handles the diverse DFA structures and efficient decomparison. Preserving functionality. Compressing the DFAs must preserve their functionality, ensuring that the compressed DFA that can still accurately process the same set of input strings as the original DFA. Balancing the comparison ratio and the speed. The comparison algorithm must strike a balance between the achieving of a high comparison ratio and maintaining a fast processing speed for the compressed DFAs. Handling diverse DFA structures. DFAs that can have a wide range of structures from dense to a sparse, and the comparison of algorithm must be able to handle this diversity effectively. Efficient comparison. The decomparison process that should be efficient, allowing the compressed DFA to be quickly restored to its original form without adding significant overhead. The Hopcroft-Crap algorithm. The Hopcroft-Crap algorithm begins with a minimal states of DFA that using a technique known as a state minimization. This process combines with the equivalent states, reducing the overall size of the DFAs without any affecting its functionality. Transition comparison. After minimizing the states, the algorithm focuses on the compressing the transition functions of the DFA. This is achieved by the identifying and eliminating redundant transitions, further reducing the memory footprint of a DFAs. Efficient implementation. The Hoopcraft Graph algorithm is designed for efficient implementation and the data structures of algorithms that can optimize both the comparison ratio and the comparison speed of the compressed TFAs. Graph-based approach in DFA minimization. That process, the Hopcroft algorithm, splits the states into partitions in order to reduce the DFA's state size. A graph that can contextually represents the states and transitions where the goal is to find equivalent states, while Hopcroft graphs especially finds the matchings in the dispute graphs. That DFA minimization finds the equivalent states by analyzing the transitions and final or non-final state groups. Equivalence classes and the matching. Just as Hopcroft's graph finds the matching the pairs in a graph. DFA minimization involves in the grouping states that behave identically under the input symbols. The concept of pairs that can be loosely throughout as a matching of states with identical behaviors used in regular languages. For regular languages, DFAs that can be used in between two DFAs that can be checked by building a product DFAs and analyzing the reachable states. This is not exactly Hoopcroft graph, but involves similar graph-based matching concepts. Optimizing the Hoopcroft graph algorithm. Heuristic optimization, parallelization, and the specialized data structures. The researchers have introduced several heuristic optimizations to the Hopcraft graph algorithm, further improving its comparison efficiency. These include techniques like adaptive state partitioning, dynamic programming, and the targeted transition elimination. The specialized the specialized data structures that can be used of specialized data structures such as compact state representations and efficient transition tables that has contributed to the algorithm high comparison ratio and the processing speed. Parallelization: the algorithm has also been parallelized, allowing for faster comparison by leveraging the power of modern multi-core processors. This parallel implementation exploits the inherent parallelism in the state minimization and the transition comparison steps. Experimental evaluation: diverse DFA benchmarks, comparison ratios, and the processing speeds. The researchers have evaluated the Hopcraft scrap algorithm on a wide range of DFS benchmarks, including both synthetic and real world DFAs, to assess its performances across a variety of scenarios. Comparison ratio: that results in the show that the Hopcraft algorithm achieves significantly higher comparison ratios compared to the existing DFS comparison techniques, often reducing to the DFA size by over 50%. Processing speed: the compressed DFS is generated by the Hopcraft graph algorithm also maintains a high processing speed with a only minimal overhead compared to the original and uncompressed DFAs. Comparison to existing techniques. State of the art algorithms. The researchers have compared to the Hopcraft's CRAP algorithm to other state of the art DFS comparison techniques such as Minded and the MRMC to demonstrate its superior performances in the terms of both comparison ratio and the processing speed. Advantages of Hopcraft CRAP. The This algorithm outperforms the existing methods by effectively addressing the challenges of preserving the functionality, balancing the comparison and the speed, and handling the diverse DFA structures. Practical accessibility. The combination of the high comparison ratio and the fast processing speed makes a Hookcraft CRAP algorithm is a practical and attractive choice for the real-world applications and that requires efficient DFA handling. Real-world applications of compressed DFAs. Text processing, network traffic analysis, or embedded systems are the main real-world applications of the compressed DFAs. The text processing compressed DFAs that can be used for the efficient pattern matching and text processing in applications like search engines, natural language processing, and the malware detection. Network traffic analysis, that compressed DFAs that can be employed for the real-time network analysis traffic, enabling the high performances and detection and identification of the cybersecurity applications, embedded systems, the small memory footprint of a compressed DFAs that can make them well suited for the deployment in a resources constrained environment such as IoT devices and the mobile applications. Conclusion and the future directions. Here the conclusion. The Hookcraft CRAP algorithm presented in the paper demonstrates a significant advance in the field of DFA comparison, offering a fast and practical solutions and addresses the challenges of the memory footprint, processing speed, and the handling diverse DFA structures. And the future works. The researchers are exploring the further optimization, such as integration with the machine learning techniques to enhance the comparison ratio and the processing speed of the Hookcraft's CRAP algorithm. Additionally, they are investigating The application of the algorithm to other areas of computer science that involve the finite automata impact. The practical advancements in a DFA comparison enabled by the research have the potential to unlock new opportunities in a wide range of domains, from text processing and the network security to embedded systems and beyond.